In this lesson, we're going to examine the notation we use when dealing with functions. We'll call it function notation. Okay, so function notation, which is f in brackets x, as opposed to y equals, is used when we're dealing with functions and we know something's a function. The way this reads is we call it f at x, and it's taken to mean what is the function value, the y value, at the given value of x. So for example, if I saw f at 2 equals 3, I'm basically saying when x is 2, the y value is 3. And we would just call it function notation. So from a previous example from a previous course, last year we looked at quadratics. We talked about the height of cannonballs over time, and we would get an equation that looked like this. The height equals. Our function notation now is going to use h at t. So the height at a certain time, t. What it's doing is it's saving us time instead of writing out words, we can use notation. So if I said something like h3 equals 12.1, I'm saying after 3 seconds, the cannonball's at a height of 12.1 meters. It just saves us that time. So how do we work this? So I have a graph of some function. I say y equals fx. I'm just saying it's some function, random function. And it is a function, it passes the vertical line test. Using our graph, I want to determine some things. I want to find f at 2. So when x is 2, here's where 2 is. Where is the function? Well, it's down here at that point. What is that point? It's negative 1. When x is negative 1, where is the function? So negative 1 is right here. I go up to the function. Oh, it's at a height of 1. F at 0, that would be right here. It's 3. Remember, our basic idea here is we're saying there's a point 0, 3 on this function. And this is your x, and this is your y. We're just doing it without having to write out points. We can combine functions and do operations between them. So if I want to do f at 2 minus f at negative 2, I've got to figure out f at 2 first, which we've already figured out was negative 1, minus f at negative 2. So if I find negative 2, I'll go up to my graph. That's approximately, what, 2.5? And then do my operation between them. I get negative 3.5. Then letter E, find x when the function is 4. So this is a different question. Okay? I want to know x when y is 4. So I find 1, 2, 3, 4 on my graph. Here's where y is 4. When is the function there? Right at that point. What's the x value? X is negative 3. So basically I'm saying there's a point on our graph at negative 3, 4. This time I was told the function value and asked to find x. And solve a graph pretty quick. You can find them pretty easily. We can also do the same thing with our equations. To use an equation, we're going to substitute our x value for all the x's in the function. For example, if I have the function 3x plus 1, and I want to find f at 3, I can put in 3 every time I see an x. So I'm going to put it in here. 3 times 3 plus 1. That gives me 10. Now stop there. One of the common mistakes is people actually calculate things. This is my answer. I don't divide by 3. I'm basically saying, remember, there's a point 310 on this graph. I just don't need to write that out, okay? We're not going to write this out. We're going to leave it in function notation. Try the next one, f at negative 2. So every time I see an x, I'm replacing with negative 2 in the function. If I do that, I'll get negative 6 plus 1, or I'll get negative 5. Okay, we can do our functions operations. So f at 5, think of this as a big square bracket. We'll do the 5 one first. 3 times 5 plus 1, minus, we'll do the next one, 3 times negative 1 plus 1. What will that give us? We'll get 16 minus, and then the next bracket's a negative 2, so we get 18. I want to find x if the function value is 4. So this function, 3x plus 1, I'm being told that the function is 4. I need to find the x that goes with it. I've basically been told the y value. In some ways you can think of this as your y value, right? we need to solve this. So 4 minus 1 is 3x, 3 is 3x, so x is 1. There's a point on a graph at 1 and 4. Now, functions can get more complicated looking. The last one was a linear function, a line. This one's a quadratic. If you see more than one x, you have to substitute in more than one spot. So when I want to find f at negative 1, I need to replace the x with negative 1 and the next x with negative 1. So negative 1 squared minus 2 times negative 1 plus 3. Or in other words, 1 plus 2 plus 3, 6. So there's a point on our graph at negative 1 and 6. And try the next one. We'll get 2 squared minus 2 times 2 plus 3. Or in other words, just 3. Again, we can do operations. So think of it as a big giant bracket. What are we going to have to do? We're going to have to do 3 squared minus 2 times 3 plus 3 in the first one, minus, we'll do the same thing for the next one. Negative 3 squared, we're going to run out of room here, minus 2 times negative 3, and then plus 3. So I ran out of room in that one. What are we going to get? Our first bracket will come out to 6. Our second bracket comes out to 15, and we can subtract. If you don't like doing big square brackets, you can do it in 2 separate parts and then subtract later. That works the same way. Okay, our next set. We can find function values for things that are not just numbers. We can do this algebraically also. It works the same way. So in this case, letter D, every time I see the letter X, I'm going to replace it with a 3a. What's that going to look like? I see an x squared, so 3a squared. I see a 2x, so 2 times 3a, and the plus 3 at the end. And then we're going to simplify. 3a squared comes out to 9a squared. Make sure you square everything. And expand, and there's our answer. It's an algebraic expression, a different quadratic. And it happened because we had variables in our initial part. We can also do operations between things. So in this case, our big idea here is that functions act like brackets. So when I see this function here inside something else, there's more parts and pieces to it, I can really think of this as saying 3 times f at negative 1 plus 2. So if I know what f at negative 1 is, which I think we figured out back here in part A, right? Here's part A, it's the same number. I know that f at negative 1 is actually the number 6. So really it's 3 times 6 plus 2, or in other words, 20. And we can do operations with functions, but a function itself acts like a big square bracket, kind of like we did when we subtracted in letter C. And if we put those two things together to try this last one here, what does this really mean? I've got a function, so a big square bracket, and I've got some algebra inside. So everywhere I see an x, I'm replacing with 2x. So we can get 2x squared minus 2 times 2x, just using our old equation, plus 3 inside the big square bracket, and then minus, oh, can't put it in there, minus 1 outside the bracket at the end. I can't really fit it in there. Hang on, let's make this smaller. Minus 1. Okay, so inside the bracket, we got to figure that out first. We'll get 4x squared minus 4x plus 3. Got the minus 1 afterwards. We can expand our brackets, so distribute. So multiply in, multiply in, multiply in. We've got negative 8x squared plus 8x minus 6. And then the minus 1 at the end. And if we simplify all that, get minus 7. Okay, so operations with functions and algebraic versions of x also. Last thing, we got to be able to write functions. So we've got this situation here. We've got Watertight Plumbing Company. They charge $45 for a service call plus $35 per hour for labor. I want to write the service charge as a function of number of hours worked. So I'm going to say T is my number of hours. So my function is defined by T. It's always $45 plus 35 per hour. There's some function. Already in the past, we thought of this as y equals mx plus b. It's basically the same idea. We're just using function notation instead. Okay, so I want it as functions now. Part B, how much are we getting charged if we work for 7.5 hours? So in other words, when time is 7.5. And we use our equation, 45 plus 35 times 7.5. And you punch that into your calculator, and I got, what did I get here? 307.5. So in other words, we're being told if you work 7.5 hours, it's going to cost this much. And that's dollars. We can put 50 cents there. Okay, if we try the last one, how much labor is required if a job costs $2.28? Well, they're telling us that the function has a value of $2.2875. How long did it take to get to that? So we can solve. Take our equation and solve it. So numbers on one side, letters on the other. We'll subtract, we'll get what? 183.75. That's 35t. Let's move this question all the way down here. Okay. And t, 183.75 divided by 35 comes out to 5.25. Okay, so it took 5.25 hours to accumulate a cost of $228.75. All right, last one. A function is defined by this equation. Determine the values of x for where the function equals 0. So by telling us that the function has to equal 0, they're saying put this in here. And I need to solve this equation. And now, this is a quadratic. And really the point of doing this question is to remind you some things about quadratics. If I want to solve a quadratic, it has to equal 0, like it does. It also wants to be in standard form, which it is. Standard form is ax squared plus bx plus c. Okay, so from biggest power to smallest power. To solve these, we have to factor. You might remember man, so multiply to the last thing. So multiply to -15 and add to -2. And numbers that do that are -5 and 3. If you haven't used man before, we still have this idea of multiplying to the last, adding to the first, or middle. Okay. Our numbers are -5 and +3. That's our factored form. Our actual answers are x equals 5 and x equals -3. Okay. Same thing for the last one. They're telling us the function. The function is 33. So I make it equal to my equation. I want to solve it. It's a quadratic again, but to do that, it has to equal 0 first. So I need to bring that 33 to the right-hand side, subtract it, to put it into the right form. I want to multiply to 48, add to -2. I can do that if I use -8 and +6. So my answers are 8 and -6. And just a reminder of some factoring and how to solve a little bit. That's the end of our function notation lesson. Some questions to try. Some of them have pictures, some of them have equations, some of them have operations amongst that. And on occasion, you have to make yourself your own function. Give it a try. If you're stuck, come see me. We'll figure some things out and keep on moving through this course.